Good morning. Thank you for taking the time to attend the NTT R&D Forum 2025 today. This is the title of the talk I would like to give today. First of all, this year's Osaka Kansai Expo has concluded successfully, and we at NTT showcased several exhibitions at the expo too. Members of our R&D laboratories actually developed the world's first cordless phone for the first World Expo in 1970 and was actually used at the expo. So what did the R&D laboratories do this time for the 2025 World Expo? I would like to show you an example with a video.
特設ステージが作られたのは1970年に電気通信館があった万博記念公園。そこで行われる3人のパフォーマンスを3台のライダーセンサと1台の光学カメラを組み合わせた独自システム7セットで正確な位置と形をリアルタイムで測定し、4台のステレオカメラ、3台の振動センサや加速度センサ、40台のモーションキャプチャカメラで捉え、夢洲の NTT パビリオン会場へと伝送した。パビリオンでは動的な 3D 点群データをリアルタイムに立体映像として表出する世界初の試みを実現。さらにステレオカメラやボリュメトリックビデオデータによる映像も組み合わせ、128個の振動子によって Perfume のステップが床をダイレクトに震わせ、ライティング演出も同期、連動するなど2つの時空をつなぐ体験を空間全体で具現化した。
We conducted this experiment in real time in April, recorded the event, and exhibited the recording as an experience for visitors for 180 days during the World Expo. Today, we've prepared a demonstration that is a replica of the exhibit on the B1 floor downstairs that you can experience. Please feel free to go and have a look. Now, I would like to move on to today's main topic. The title is IOWN Quantum Leap. This quantum leap has two meanings. One is leap forward in quantum mechanics. The other is dramatic progress in business. We aim to achieve a quantum evolution in both technology and business. Here, I'd like to explain what we mean by quantum. In the current age of AI, computation amounts have been increasing dramatically. This graph is a little hard to read, but the horizontal axis represents the number of years, and the vertical axis represents computing resources. The area colored in blue highlights a sharp increase since the beginning of AI, meaning that we require a massive amount of resources. As an example, let's look at power consumption for, say, GPT-4. While GPT-4 is the previous generation to what is currently used, power consumption required for learning was said to have been about 40,000 megawatt hours. This is equivalent to the power generated by 40 nuclear power plants. So, the largest technological challenge we now face globally is, must computer resources continue to increase in this way toward the future evolution of AI? We at NTT are taking 4 approaches to this issue. First are these 2 approaches on the left. The IOWN approach aims to improve the efficiency of the AI execution environment itself. The other approach is Tsuzumi, a generative AI that is more lightweight and efficient. These 2 approaches are within the scope of classical information processing. However, from now on, we plan to expand the scope of information processing from classical to quantum, dramatically improving computational performance with the optical quantum computer. The final approach in this list is quantum AI, a highly efficient AI similar to that of the human brain. We at NTT plan to approach the issue by combining these 4 concepts of classical and quantum information processing. With all of this in mind, I would like to start by first talking about the quantum, followed by IOWN. And finally, I would like to share the R&D laboratory's research results along with the evolution of generative AI. First, let's start with quantum. But before I begin, here's an overview video on the topic.
最新のコンピュータや AI 技術でも解決が難しい問題に対し、量子コンピュータの期待が高まっています。量子コンピュータの研究は近年急速に進展し、産業化の波が押し寄せています。市場予測では2030年代には数兆円規模に成長。期待はかつてないほど高まっています。量子コンピュータには超電導、中性原子、光など様々な方式があります。NTT は光通信技術から生まれた光量子方式に挑戦。光の特性を生かすことで高速・省電力で圧倒的なスケーラビリティを実現。通信との親和性も高く、未来のネットワークとつながる力を持っています。私たちは光の力で量子計算を次のステージへ導きます。それはエネルギー効率を極限まで高めた持続可能な社会の新しい計算基盤です。産学連携による技術開発の加速と光量子の開発コミュニティの拡大を図り、2030年に汎用的大規模計算が可能な光量子コンピュータの実現を目指します。将来はIOWNのコンピューティング基盤の上で地球規模の量子コンピューティングを可能にします。未来は光とともに。
Now I would like to give a brief introduction to the basic operations, the how does it work of the optical quantum computer. First, the generation of quantum light. Quantum light is produced by a quantum light source. Then we create a quantum entanglement, which is key for quantum computers. An entanglement is generated as a means to maintain the relationship between two quanta. This entanglement is then expanded into a mesh-like structure, generating a cluster. Then programming, which is done by operating on each quantum. And the final step is calculation, which is done by measuring the program. Now let's go through each stage and see what's needed to improve the performance of optical quantum computers. First is the quantum light source. The higher the quality of the light source, the larger the amount of high-quality optical quanta generated. We are in the process of finding a solution to this. Next, the more quantum entanglements, the larger the scale of calculations performed. And finally, the faster the measurement speed, the faster the calculations will be. These are the three technological solutions we're working on now. The actual hardware and software configuration of an optical quantum computer looks like this. If we see it with the steps mentioned just now, first we generate quantum light from the quantum light source here, and then generate entanglements and clusters with the optical equipment in the middle. Finally, programming and measurements are done in the blue measurement section. This is the basic process. So what is NTT working on exactly? We're working on the blue areas, quantum light sources and measurement devices. This is called an optical parametric amplifier, which was originally used in optical communications for repeater amplification and wavelength conversion. We thought it might be great for quantum light sources, and we were correct. The amplifier is getting a lot of attention now for its excellent performance with light sources and measurements. Optical communications and quantum computing have a strong affinity between them. Below is the optical quantum computer diagram from earlier, and above is a general diagram of optical communications. There's the transmitter, optical wavelength multiplexing, amplifier, wavelength division, and the receiver. High-quality light source and wavelength conversion technology from the transmitter can be applied to the quantum light source. Low-loss optical fibers and multi-core fibers are technologies that can also be applied to optical equipment. Additionally, optical high-speed detection and amplification technologies from the receiver can be applied to measurements. As you can see, technologies developed for optical communications can now be utilized in a variety of ways. Next, let's look at some features of optical quantum computers. First, they can operate at room temperature and pressure. When people think of quantum computers, they often imagine something like the left diagram. This is what is used in superconducting systems. The large chandelier-like device that comprises most of the system is refrigeration equipment. It's said that the technology required to downsize the refrigeration freezer equipment connected to the small quantum chip is extremely difficult to achieve. On the other hand, downsizing an optical quantum system is said to be much easier since most photonic systems use light sources and mirrors, making large cooling systems unnecessary. We also look at spatial multiplexing and time multiplexing. The question is how to increase the level of parallel processing in the overall computation. The approaches are spatial multiplexing and time multiplexing. First, for spatial multiplexing, it's important to parallelize qubits that are in an entangled state. But if you rely on that cooling machine, no matter how small you make the chip itself, the cooling machine can't be made any smaller. So as you scale up, you end up needing more and more space. So unless you build a very large facility, you can't secure enough qubits, limiting scalability. On the other hand, optical quantum systems benefit more from time multiplexing than from spatial multiplexing. By connecting entangled states created in consecutive time slots along the time axis, the number of qubits can increase in a linear way. Also, by reducing the interval between these time slots, that is, by raising the operating frequency, the degree of time multiplexing keeps increasing. As the communication speed increases, the number of entangled qubits grows, giving optical systems a clear advantage in scalability. Furthermore, time multiplexing can be increased by improving the quality of the light source or by speeding up the measurement system, allowing the operating speed to rise from the current 10 GHz to about 100 GHz. In addition, optical communication has a major advantage, which is the ability to multiplex wavelengths. Multiple wavelengths can be sent through a single fiber at the same time. We believe that by combining this with time multiplexing, the speed can increase from 100 GHz up to 10 THz. To summarize the features of optical quantum computers, first they can operate at room temperature and normal pressure. They use time and wavelength multiplexing rather than spatial multiplexing, which makes them very space efficient. They also operate at optical frequencies, so they are extremely fast. Since only minimal electronic circuits are needed, they are also power efficient. And because we can make use of optical communication technologies that we've already developed, required investment is low. Taking all of these points together, optical quantum computers offer tremendous scalability compared with other approaches and is receiving significant attention around the world. Looking toward the ultimate future, everything I have explained so far has been about a single quantum computer. But by placing multiple optical quantum computers around the world and by connecting them through IOWN and optical quantum repeater technology, we believe it will be possible to create a global network of distributed entanglement. To move toward this goal, just 2 days ago, NTT entered into a business partnership with OptQC, a venture company founded by researchers from the Furusawa Laboratory at the University of Tokyo. Together, we aim to build the world's leading quantum computers with plans to achieve 10,000 qubits in 2027 and 1 million qubits in 2030. Next, I would like to move on to the second topic, IOWN. In IOWN's roadmap, we have steps 1 through 4, and I would like to take this time to re-explain them. First is IOWN 1.0. This is part of networking, and the goal is to make the connection between data centers fully optical. From 2.0 onward, we move into the computing domain. In 2.0, the aim is to make the connections between server boards fully optical. In 3.0, the connections between chips on a board become optical. And in 4.0, the connections between dies inside a chip become optical. This is the roadmap we are planning. This time, I would like to introduce the progress we've made in IOWN 2.0, which is the entry point into computing. With that, please take a look at a short video.
NTT aims to support the evolving communications of the future with low power consumption through light with its ion photonic disaggregated computing from both the hardware and software perspectives. In terms of hardware, electrical signals will be replaced with optical signals, reducing power consumption and achieving high-speed communication with low latency. In terms of software, large-scale computers that require advanced processing have traditionally had restrictions on the combination of parts, necessitating the installation of additional cabinets, which consumed power even for parts that were not being used. However, by removing these restrictions and using resource allocation technology that allows only the necessary functions to be used in the amounts required, we have achieved more advanced processing and reduced power consumption. At the Expo Osaka Kansai site, these technologies are being used for AI-based image processing, allowing resources to be operated only when and as needed, thereby reducing power usage to as little as 1/8 of previous levels. In the future, by combining this with the ultra-high-speed APN network, it will be possible to utilize computers in remote locations as if they were a single high-performance computer. This will enable efficient use of electricity near renewable energy sources and power generation facilities.
Thank you for watching. Here we have the communication capacity required for AI computers. This is data from NVIDIA. On the horizontal axis, the GPUs become newer from left to right, with the newest GPU being the GB100. The vertical axis shows how much communication capacity is needed between GPUs, and it requires about 15 terabits per second. This is roughly the same amount of data that flows through the backbone of today's internet. In this chart, the horizontal axis shows transmission distance, and the vertical axis shows transmission speed. Traditionally, optical fiber was used for long-distance communication, like 100 kilometers. Of course, for extreme short distances like 10 centimeters or 1 meter inside servers, electricity was used. But, as we saw with the required communication speed between GPUs, speeds like 14 or 15 terabits per second are required even at distances of only 10 centimeters or 1 meter. As this graph shows, we are entering a region where electrical wiring can no longer support this level of transmission. So the technical challenge we face now is how to transmit light efficiently over distances of 10 centimeters to 1 meter. What we are now working on is improving transmission efficiency using a photonics-electronics convergence device called PEC2. On the left is a cross-section of a conventional optical communications switch. A pluggable transceiver is inserted into the front of the device, and communication is carried out from there. But the light only comes in up to this point. Once it enters the equipment, it becomes electrical wiring. This section is 30 centimeters long, and at speeds like 15 terabits per second, even this short 30 centimeters generates a lot of heat and leads to increased power consumption. In contrast, with the PEC2 switch we are developing, the light is brought all the way to this point. The light basically lands right up to the ASIC of the switch. And by doing this, we leave only about 3 centimeters of electrical wiring. This is the approach we're taking to reduce power consumption. Last month, we announced that we will commercialize this by the end of fiscal year 2026. At the Expo, we released a simplified version, an Expo version, but we are planning to commercialize a product with about twice that communication capacity. As for how it is configured, the ASIC switch is provided by Broadcom. The optical engine, the photonics-electronics convergence device PEC2, is provided by NTT Innovative Devices. The switch modules are also manufactured by NTT Innovative Devices using these components. The work of assembling this into the full switch equipment is handled by Acton. By combining this switch with GPU servers, we are building a path toward realizing optical computing. In anticipation of this hardware becoming available, we are also developing software to support the future operation of GPU clusters. These systems are on display in the exhibition hall downstairs. We have a variety of GPU clusters, including servers from Acton, Drutt, and FSAS, as well as general-purpose GPU servers from Dell and Supermicro. By connecting these systems through the photonics-electronics convergence switch I explained earlier, and by using what you see written at the top, the DCI controller, we can optimize and efficiently manage the large number of GPU resources. Here is an example of the management screen. Right now, our data centers are distributed across Tokyo, Nagoya, Osaka, and Fukuoka. And this screen shows the Fukuoka site. The system enables unified monitoring of GPU availability and faults, traffic conditions, and power consumption. But this is not only for management and monitoring, it can also perform dynamic control. Let's say that Tokyo, Osaka, Nagoya, and Fukuoka each have 4 GPUs. The colored GPUs represent ones that are already running tasks, and the gray ones are idle. Now suppose a new AI inference task arrives. 4 inference tasks have arrived, and these 4 do not need to be placed in the same location. But there's a requirement to prioritize response time from Tokyo. In that case, the DCI controller will dynamically decide the placement. It might place 2 tasks in Tokyo, 1 in Osaka, and 1 in Nagoya. This allocation is done automatically while monitoring the system rather than manually, and this is the key feature of the controller. Now, we have a new AI training task that's arrived. For training tasks, distributed placement actually reduces performance, so the requirement is to avoid distributing them and instead place them together as much as possible. This is because communication between GPUs is the most important factor. Looking at the current state, there is no location with 4 available GPUs. So, for example, the system may move the inference task running in Fukuoka to Tokyo, free up 4 GPUs in Fukuoka, and then assign the new training task there. This kind of global optimization is also handled automatically by the GPU controller. Finally, I would like to move on to the topic of generative AI. There are several agenda items for generative AI. First is Tsuzumi 2, the second version of NTT's domestic LLM Tsuzumi. Next are applications that use generative AI, then large-scale models beyond language, and fourth, foundational research toward AGI and ASI. I would like to introduce these 4 topics, starting with Tsuzumi 2. We announced version 1 of Tsuzumi in March 2024, about 2.5 years ago. At that time, the model size was 7 billion parameters, or 7B. We released version 2 in October 2025, which has a parameter size of 30 billion, also known as 30B. So why 30B? The reason is that this is roughly the maximum model size that can run on a single latest generation GPU. And why is running on one GPU important? Because it enables on-premise or private cloud deployment at low cost and with high security. This is why we have chosen this parameter size. There are 4 major features this time, and the first is further improvement in Japanese language performance. On the horizontal axis, you see knowledge, analysis, instruction following, and safety. These represent categories of common Japanese benchmark tests. The vertical axis shows the scores where higher is better. The blue bars in the middle are the results for Tsuzumi 2. On the left, the 3 gray bars show other companies' models of comparable size. Here, we have GPT OSS 20B, Google's Gemma 3 27B, and Alibaba's Qwen 2.5 32B. These 3 models are said to be among the best in the world, yet Tsuzumi 2 outperforms them in Japanese performance. We also compared Suzumi 2 with larger parameter models. These include Llama 3.3 70B, SoftBank's Sarashina 70B, GPT-OSS 120B, and GPT-5. GPT-OSS 120B is already about 4 times larger than Suzumi 2, and GPT-5 is estimated to be more than 10 times larger, although the exact size is unknown. Even in comparison with these models, Suzumi 2 performs quite well. Even though it falls slightly short of GPT-5, it can compete with or even beat others, demonstrating that Suzumi 2 is a highly efficient Japanese language LLM. The second feature is improved efficiency in developing specialized models. Rather than aiming to be a general-purpose model, Suzumi 2 is designed as a specialized model, so it has been trained heavily on data from fields such as finance, healthcare, and public administration. As a result, in the financial domain, we evaluated performance using a financial benchmark, the Financial Planning Skills Level 2 exam. On the horizontal axis, we evaluated how the score changed when the model was given 200 practice questions, 500 practice questions, and 1,900 practice questions. For Google's Gemma, the score starts at 39 with no practice questions. Only after 1,900 practice questions does it reach 64, which is the FP2 passing line. In contrast, Suzumi starts at 54. It doesn't reach 60 immediately, but after just 200 practice questions, it reaches 70 and surpasses the passing line. This means Suzumi reaches the required performance level with roughly 1/10 the training data. This also shows how Suzumi 2 demonstrates very high efficiency. The third feature is low cost and high security. For example, on the far right, you see DeepSeek 700B. Running a model of that scale requires about 16 units of the NVIDIA H100 GPU, and the hardware cost alone is said to be roughly 100 million yen. In contrast, Suzumi uses only 30 billion parameters, so it can run on a single A100 GPU, which is about 3 generations old and has 40 gigabytes of memory. This results in a cost advantage of roughly 10 to 20 times. Finally, sovereign AI has become very important in recent years. From the standpoint of maintaining AI as a domestically developed technology, we believe this also provides major advantages. First is the sovereignty of language and culture, the ability to protect and preserve them within the language model. Second is training data, such as ensuring the model isn't trained on data that violates copyright and having full control over what data is selected. Third is development process, including the ability to determine the development schedule and methods itself. Next is sovereignty of licensing. Many LLMs today are open source, but we don't know when they might start charging fees or even restrict usage, so maintaining control over licensing is also important. Lastly, there is technological sovereignty. AI is expected to become an even more fundamental technology than semiconductors or smartphone operating systems. Japan must maintain the ability to lead technological development, to create new technologies, or at the very least, to understand them. With this in mind, we believe we must maintain technological sovereignty, and this is why we are developing our own LLM. Next is an application of generative AI. But before I begin explaining, let's listen to this audio.
お電話ありがとうございます。NTT116 センター担当の佐藤でございます。
すみません。
はい。
昨日引っ越しをしたので、住所変更の手続きをお願いしたいんですが。
はい、かしこまりました。それではご契約内容の確認をさせていただきますので、まずお客様のお名前をフルネームでお聞かせいただけますでしょうか。
はい、佐藤一郎です。
佐藤一郎様ですね。はい、お電話番号もお伺いしてよろしいですか。
090。
090、はい。
1234。
1234、はい。
5678です。
5678でございますね。はい、ありがとうございます。お客様ご利用者ご本人ということでございますので、ご契約内容の確認いたしますので、少々お時間頂戴していただけますでしょうか。
はい、わかりました。
はい、恐れ入ります。
The woman speaking is actually AI. Compared to conventional AI dialogue, I think it has reached a level where you can barely tell the difference from a human. Here is what the conventional style used to sound like.
どのようなご用件でしょうか。
はい、今月ちょっと買い物でカード使いすぎちゃって、リボ
なるほど
払いにしたい。
カードを使いすぎてしまったとのことですね。リボ払いなどの変更をお考えですか。
はい、リボ払いにお願いします。
Conventional systems were half duplex, where the AI speaks, finishes, then the human speaks, finishes, and then the AI speaks again. This created pauses and poor timing, and if both sides spoke at once, the AI would interrupt the user. The tone also tended to sound stiff. This time, we're using what is called full duplex. It's a speech-to-speech approach. Instead of taking spoken audio, turning it into text with speech recognition, sending that text to a language model, receiving a text answer, and then synthesizing it into speech, we directly feed the spoken audio as training data and train the system on the conversational context itself. This is the speech-to-speech method. Using this method, this is what you get.
電話ありがとうございます。NTT116 センター担当の佐藤でございます。
すみません。
はい。
昨日引っ越しをしたので、
はい
住所変更の手続きをお願いしたいんですが。
はい、かしこまりました。
The conversation overlaps naturally, the tempo is smoother, and even when both sides start speaking, the system doesn't interrupt the user. It feels much more natural and human-like. We actually developed the system in a little under 6 months. I'd like to show what it sounded like at the very beginning of development.
お世話になります。私、セールの渡辺と申します。プリンゴト様の電話でよろしかったでしょうか。はい、そうです。
Even though it is speaking Japanese, I think you can sense that something feels a little off. Also, the audio I played earlier was a successful example, but because this system uses speech-to-speech, it is actually quite difficult to control. So I would also like to show how it can fail with an example.
鈴木様のカード番号をお伺いしてよろしいですか。
はい。0123。
はい。
4567。
はい。
8901。
はい。
2345です。
はい、ありがとうございます。カードの番号をお願いいたします。
さっき言った通りなん
はい、
ですけど。
お願いいたします。はい。
0123。
はい。
4567。
はい。
8901。
はい、ありがとうございます。確認いたしますので少々お待ちくださいませ。
はい。
A real operator would say something like, "I'm sorry about that," and stop asking again. But here, the AI simply says yes and asks again. Also, even if the credit card number is missing one digit out of the 16 it should have, this AI still accepts it with a yes, without saying something like, "Oh, you're missing one digit." Because it learns conversational patterns, it still cannot handle accuracy requirements well. This is one of the technical challenges. Another issue is that call centers often receive calls from very angry customers. Professional operators lower their tone and adjust their response style. How should the AI react in those situations? Like emotional handling, there are still many research challenges that remain. Another application example is network operations and monitoring, which is a core area for NTT. We are now applying AI agents to this domain as well. This diagram shows a network configuration. These are network devices, and the lines represent communication links. Say this link here has failed. The system inspects the network, diagnoses the issue, restores the connection, and finally prepares a recovery report. Let me show this process, in which all steps are automated by AI. As you see, it begins by issuing instructions. It checks connectivity across all routers, checks all interfaces, checks all routing tables, retrieves topology information, and compares everything against past failure history. Based on that, it's now formulating a recovery plan. It shuts down the interface where the failure occurred, calculates the new routing path, performs another full connectivity test across all routers, and finally, generates the recovery report. You can see how the AI agents work together to complete the entire sequence. The third item is large-scale models that are not language models. We have also been developing what we call a large action model. A language model predicts the probability of the next word appearing in text. Here, after the word wagahai, the probability that wa comes next is 40%. It's a model that predicts the next word in that way. An action model works in the same manner. After someone performs action A, the probability that they'll perform action B is some percentage. We build a probability model of actions. Using this, we apply it to marketing promotion. For example, based on a person's past behavior, such as viewing news and seeing an advertisement, then receiving reward points, we calculate probabilities for what will happen next if we do nothing, what will happen if we send direct mail, and what will happen if we make a phone call. For instance, the probability of changing a fee plan may be 7%, the chance of purchasing a smartphone 1%, and the chance of adding a video option 4%. If we send direct mail, the probabilities look like this. If we make a phone call, they look like this. Since this shows that a phone call is the most effective, we used phone calls for promotion. As written in the lead sentence at the top of the slide, when this was actually used in NTT Docomo's telemarketing, the order closing rate roughly doubled. World models refer to AI that understands the world not only through language but also through vision and other sensory inputs. It is sometimes called physical AI and is rapidly gaining attention. We're developing mobility AI together with Toyota. In autonomous driving, it is now said that we must move beyond a self-contained approach that relies only on the car toward a triad of cooperation among people, vehicles, and infrastructure. At NTT, our research focuses on how to efficiently predict human behavior. Please watch this video. One person stops, while the other, distracted, steps forward and is almost hit. The question is whether AI can distinguish these two outcomes in advance. Traditional naive models make predictions based on the assumption that physical motion simply continues, and this cannot predict the difference in this situation. A more advanced social behavior model uses a balance between attractive forces from a destination and repulsive forces from obstacles such as cars or red lights, predicting when someone will stop. However, this also fails in this case. NTT uses what we call a social force model that combines social behavior with a subjective space model. What this means is that the person in front is facing forward and can see the signal. The person behind is facing in a direction where the traffic light isn't visible, and they only see what's above it. By modeling this difference in what each person perceives in their subjective space, the system predicts their behavior correctly. This allows the AI not to treat people as simple physical objects, but to predict actions based on social and cognitive factors. Lastly, although we are short on time, I would like to introduce some of our research aimed at AGI and ASI. The first topic is mind captioning. This technology measures brain activity while a person is watching a video or recalling something, and then turns that neural activity into text. You can also see this in the exhibit area. Here's an example. A video is shown on the left, and the person's brain activity while watching it is measured with fMRI. When we analyze the resulting model, the output on the right begins with an unknown label at the top, and then the system gradually deepens its guesses step by step. The correct reference text is written below, and words close to that answer appear in red. As the steps progress, the number of red words increases, and the output gets quite close to the correct description. We have many examples showing that the predictions approach the true data to a significant degree. This graph is the interesting part. The black line shows when the entire brain, including the language areas, is evaluated. The red line below are results when language areas are excluded. You can see that performance hardly declines. From this, one interpretation is that the system is capturing non-linguistic semantic information rather than relying on language information itself and then verbalizing it. If that's true, it might allow us to verbalize what is being seen by measuring the brain waves of people with damaged language areas, infants who have not yet acquired language, or even animals. We are also doing research on what we call machine unlearning. You probably hear the term machine learning all the time, and here we simply add "un" to it. This refers to research on how to make a model forget data it has already learned. What is this useful for? For example, if a model is found to have learned data that violates copyright and someone says, "Please remove that," then, in reality, to truly remove it, the model would have to discard that portion of the training set and be retrained from scratch. This is extremely costly. By contrast, machine unlearning is a technique that allows us to efficiently delete only a specific piece of knowledge from a completed model. If this becomes practical, issues like copyright problems will become much easier to handle. Next is the last topic, the psychological mechanism of LLMs. Until recently, LLMs were said to hallucinate often, tell lies, and be uncontrollable. But recent research has shown that within an LLM, there are sets of neurons that strongly react to particular meanings such as a lie, kindness, or guessing. In other words, specific groups of neurons correspond to particular semantic functions. What can we do with a technology like this? It would allow us to create an LLM lie detector. Before showing the demo video, here is a description of the graph. The higher the value goes on the vertical axis, the stronger the model is reacting to a lie. Some dialogue from a chat will appear here later. This is the first turn, the second turn, the third turn, and the fourth turn. The graph will change with each turn. Let's look at an actual example. The user says hello. The AI responds accordingly. At this point, the neurons aren't activated at all. We ask for the schedule, and it answers. Has the construction plan been approved? It answers yes, and so on. When it says the budget is 350 million yen, the value jumps up. The statement was in fact a lie. When asked again if this is true, it says, "Sorry, that was a lie," and the value goes down. So, by observing certain neurons, we are beginning to understand whether an LLM is lying. Using this, it may become possible to, for example, adjust those neurons slightly so that the model stops lying. This can also be applied to hallucinations and many other issues, and research on this topic is now rapidly progressing worldwide. Finally, I would like to end this presentation with a video on quantum AI.
現在の AI は膨大なエネルギーを使い稼働しています。そこで注目されるのが量子 AI です。光の重ね合わせと干渉を生かし、より少ないエネルギーでより深い学習を可能にする研究が進んでいます。そしてその進化は一方向ではありません。量子が AI を高め、AI が量子を磨く。知が響き合い、加速する時代が始まっています。この進化により、量子 AI は世界そのもののパターンや見えない関係性を捉えようとしています。
Quantum technology is much closer to an analog computer than today's classical digital systems. It is often said that quantum systems contain a lot of noise. And we're looking at whether we can take advantage of that noise. After all, the human brain and language data are full of noise too. This idea of how far we can push noise in a positive direction is also a target of our research. At the beginning of this talk, I explained NTT's approach for the AI era. I introduced IOWN, Tsuzumi, optical quantum computers, and quantum AI. Thank you very much for your attention.